the anchor has to be strong, substrate has to be strong, and glass itself has to be glazed with protective film. Film has to have certain thickness and capacity so that it flexes, it develops membrane action, but it does not let go. But in most offices, we have, of course, exterior glass cladding. Here you see Singapore Airport curtain wall system, which has blast protection or blast resistant glass. These glass have two layers of plastic inside. They're all glued together, and plastic is glued to the glass, and glass starts cracking, but plastic keeps them together. They're referred to as blast-resistant windows. What happened was, it was a US manufacturer. They made a mistake. Instead of putting 2 layers, they put 1 layer. So then the construction stopped in Singapore. They asked us to test to see if 2 layers and 1 layer would work, and we tested them side by side. They behaved the same. So if you go to Singapore Airport, these are the glass windows that are covering exterior of the building. In most office buildings, we have aluminum mullions, these aluminum frames with glass in between them. And if the entire building is covered, as you know, they're called curtain walls. So curtain wall systems are quite commonly used in modern construction. Office buildings, embassies, and other critical facilities, they do use curtain walls, mullions, so this is becoming very, very important problem. The other protection systems that we tested are, as I mentioned to you earlier, sometimes if they feel that they cannot strengthen the panel or the building envelope, then they put catchment system. So they accept failure, but so long as failed pieces are caught by a mesh, so that they don't let go and kill people. So this catchment system was made by Guardian Coil Protection System company in the US, and we tested them. And again, this was a Global Affairs or Foreign Affairs Ministry project, and we tested windows. As you can see, this time window failed, but all the glass, with the exception of smaller pieces, were contained with the catchment system. And then we tested also masonry wall. They can be made to be very, very strong so that they can capture even pieces of block masonry. So there are different applications of these protective systems. I showed you earlier window shades, and then here this is Guardian Coil catchment system. These are external devices to help you protect the occupants, or you can increase capacity of windows by protective film, but that's not enough. If film doesn't fail, then anchors may fail, the wall may fail, so you have to be careful. We developed a design software for window design, and we also developed S852 standard for window protection. Currently, we're working on a design procedure for curtain walls, and hopefully that will be available for people in the industry to use. Once again, thank you for your attention. I know we're running late, but I wouldn't mind taking 1 or 2 questions if you have them. Thank you. Yes. Depending on the failure mode, you have to anchor them. If it's flexural failure mode, obviously strengthened wall wouldn't help. But the previous case I showed you, we did not have to anchor them because we were after increasing arching action. So if it didn't deflect too much, it would develop too much arching action. But the reinforced polyurea one, we welded reinforcement top and bottom. The argument being it would be anchored at the floor level. The very last Singapore Airport project I showed you, the laminates, the plastic inside were extended. They went into the concrete floor. They said that they were going to cast concrete on top of that, so it was well anchored. Right? But this is a very valid question, of course.
And another one is about making the city longer. How do you make that?
Period longer?
Yeah, you said that is
Yeah, but-
airports.
Yes. Okay. Yeah. So that is related to the shock tube capability. Shock tube driver section consists of a whole bunch of cylinders. The longer it becomes, the longer the duration is. So this is how we control. Those two parameters, pressure and duration, are controlled by the level of compressed air that controls pressure, and the length controls duration. Because if it's longer, then it goes for a longer time.
Like polyurea thickness. What is the thickness of that?
Okay, polyurea thickness is 3 millimeters. Because it hardens right away. It's applied at very high temperature. As soon as it hits the material, it hardens, and you have to be skilled labor. You provide 3 millimeters, and then you can have second 3 millimeter layer. Altogether it becomes 6. For the first wall we had 3 millimeters. When we reinforced it, we used 6 millimeters.
Polymer based or
It's polymer based. I am not sure, because the equipment they use, the pump they use, has to handle fibers. Just like in fiber reinforced concrete, it may ball up and it may not be sprayed, because they spray through small nozzles. So they have to, theoretically you should be able to, but you have to have appropriate nozzle, I suppose, just like shotcreting fiber reinforced concrete. Yes.
I think optical property is very important here. If you put fibers, then maybe you will change the optical properties. And my question is, what is the other criteria, for example, the lifetime for this plastic laminate?
Okay, so polyurea appeared to last a long, long time, because they use it for truck bed liners against corrosion. They put it in acid containers, you know, those trucks that carry acid, fuel. Inside is applied with polyurea. So they are corrosion resistant, and then they are known to have long life. But anything other than that, I can't give you numbers as to how long they will last. But this is what they did in the U.S. Pentagon, is applied polyurea after 9/11. Yes.
Do we need to do some conversion between the shock tube test and the open test that we have seen?
No. A shock tube test gives you exactly the kind of pressure distribution you get in real life. In fact, the advantage of using shock tube is it's reproducible. You want to do 5 tests using same pressure time distribution, you can get exactly 5 same distribution. But in blast tests, it's very difficult to control. Right?
It's not directed through this structure is directed through the shock tube.
That's right, but this is why I meant to ask a question to previous researcher. I was wondering if the reason why they couldn't fail panels was there was wraparound effect. So if you have a column, this is typical in bridge columns, right? If there's detonation, it does push the column, but immediately pressure goes around, wraps around the column, it starts helping you. So you have to close, like in a real building, it doesn't go inside the building and help the panel, right? Because it's enclosed. So I suspect if they covered sides of those walls, maybe it would help, because your pressure hits the wall, but immediately it engulfs the pressure, and then it helps you. This is called wraparound effect. It may have helped. So in shock tube, the fact that we don't allow wraparound effect is an advantage. It simulates real behavior.
How much cost?
We spend about $500,000 Canadian dollars, so it's about 400,000. But it can be produced. This is not rocket science. Anybody can make it, right? It can be customized. All you need to do is get some mechanical engineers who can do CFD, computational fluid dynamics, and then determine the thickness of the steel. In our case, we were lucky because it was built by Baker Risk, American company in Texas. They didn't want to move that steel, so they bought it locally. A local company promised them. They ran out of the thickness that they have. They provided 3 times the thickness. So we have extra capacity, for which we didn't pay. So, you know, I lived through that experience, so I know it's not, I mean, if you know how to design a pipe that doesn't burst under that pressure, you can do it. And then the only other technology you need is remote control, which is not a big deal, right? So, of course, you can't control it next to it. Our last lab is at the basement level, and then control is on the first floor. But even then, we wear protective devices, and the entire building shakes. So it's a big deal, but technologically, it's not a high-tech testing facility. Yes.
For any blast, there is a dynamic effect and shock wave, right?
Yes.
We design on the dynamic effect regarding the shock wave is a little bit regarding the what if both of them came together? Like the
Okay.
blast.
They don't come together because shock wave travels much faster.
Yeah, I know. But what if there is a blast with the dynamic effect and the shock wave, and there is another blast with the dynamic wave and shock wave, and the dynamic from here and the shock wave come from here, and they came together? It might happen.
So for that hyperbolic pressure has 2 components in it.
Yeah.
One of them is shock wave, the other one is dynamic pressure. Okay? Dynamic pressure comes later, and it forms the bottom half of that parabolic distribution, right? So then the shock tube can simulate actual effect the way it happens. The only problem we experience with shock tube is the pressure goes and hits the specimen, comes back and hits the back of the shock tube, comes back again. So there are usually second peaks. If you don't mind having small second peaks, I think shock tubes are very functional, very good to use.
Okay. Well, yeah, we have questions.
Please, I saw one strengthening FRB by Anchor. Is this method in the ACI code?
It is not in the ACI code. You mean ACI building code or ACI blast strengthening?
ACI 440 for FRB.
440. 440 is not for blast, but for FRP strengthening. Yes, they do have it. They make reference to glass fiber anchors. We developed carbon fiber anchors. So it is available commercially. If you want to buy glass fibers, people are using it. It's available. And 440 document makes reference to it.
In 440, not in
440 is a FRP rehabilitation document, not for blast. Yes.
After you study the building after bomb camp, you consider this element in non-linearity or still linear?
Oh, it depends. If, like I showed you earlier, slab, which deflected linearly, bounced back. That is linear. But if there's permanent deformation, that's inelastic. So when we do, I guess I know where you're getting at. When I said you can do single degree of freedom analysis elastic, I didn't mean to imply that you always do that. Those load mass factors are available for inelastic behavior as well. So stiffness goes and yields. You have flat yield plateau. It unloads. It has hysteresis loop. You can build that in your computer program. In fact, the other RC Blast program that we have has it. and the outcome is strength and ductility. It tells you how far inelastically it went. Okay, so what I showed you is the simple elastic analysis. First thing you do, the moment you exceed capacity, next time you have to do either inelastic or you increase capacity if you want a high level of protection.
Okay, thank you very much, Professor.
Thank you.